Hello, and welcome to my presentation on knot theory. Today, we'll be talking about random braid words and their link properties. So, it's well known that braids can be very easily used to generate links. And as seen in our group report, this can be done by taking tops and bottoms of strands in a braid and joining them so that they form closed loops. But this doesn't uniformly represent the sets of links or planar link diagrams, which is evident since braid words can produce Reidemeister kinks, but they cannot, by definition, produce Reidemeister type 1 kinks. So this introduces bias into the link properties that arise from this method of generation, and therefore this has to be studied and understood before implementing algorithms that rely on these properties. So first I'd like to introduce some basic braid theory. This is the algebra that will help me outline how we can manipulate and construct braid words. So a braid word is a sequence of generators, algebraically in a product, where each generator represents a level of the braid where there's just one crossing. So for example, if sigma I represented this and sigma j represented this, then the product sigma I, sigma j would represent the stacking of these two from top to bottom, which would look like this. We look at this more closely in the individual reports, but the set of n-strand braids form an algebraic group. These are just three commonly used relations that we can use to manipulate and simplify braid words. So the first one is self-evident. It's the cancellation of consecutive inverses and is an example of the Reidemeister type 2 move. The second one describes how crossings with no common strands can be shifted vertically up and down without harming the form of the braid. And the third one, similar to the first, is an example of the Reidemeister type 3 move, but we will not elaborate on that for the scope of this presentation. To move on to the more practical side of things, we consider that a random braid word is a sequence of independently randomly chosen generators. We realize that this is very different from choosing a random braid. As I showed in my report, if you're choosing 4-strand braids of length 4, over half of these will be immediately simplifiable by just the consecutive inverses relation on the previous slide alone. Here are some basic properties of the definition. So the expectation of the linking number and the right is 0 due to the existence of inverses, and each inverse has a negation of the crossing signs of its counterpart. The variance of the right are calculated to be the length of the braid words being generated, and I also found the distribution of the right is a transformation of the binomial distribution given by the probability here. So the other link properties didn't come about so easily mathematically, so I had to use computational methods in order to analyse those, such as the Jones polynomial. To do that, I first wrote code to generate a random braid word, as defined earlier. Then I wrote code to convert the braid back to planar diagram notation, which was a class object used in the group project. Then I, after seeing the data, I thought it was a good idea to group it by the number of components that closing the braid formed, which you'll see in a minute. And then I wrote the script to generate 200 samples of braid words for each length between 1 and 12. These graphs show the mean number of terms in the Jones polynomials of 3 and 4 strand braids against the word lengths, which I calculated using the Jones function in the group project. The overall data, which is in black, is roughly linear, and despite some anomalies, you can see so is the data in the individual groups. You'll also notice how only the even lengths give the maximum number of components. This is because odd lengths mean that 2 strands formed an enclosed cycle. Also, you'll see how groups are in the sequential order until around length of 8, where the lines start crossing. Interestingly, for both graphs, the mean for the 2-component links act very similarly to the overall data. One more thing I did notice about the categorized data is how the first 2 data points of each category of the 3-strand braids and the first 3 data points of the 4-strand braids are all kind of on horizontal lines. Now that's really curious to me, so I did try the 5-strand braids, and I saw a similar theme of there being the 4 data points on horizontal lines, which is really counterintuitive. I expected that region of the graph to be the steepest slope, since there would have been the least inverse cancellation there. So that does deserve some more investigation in the future. When making a braid in the real world, it'll lose complexity if two taut strings are crossed and uncrossed at any 2 points in the braid, as long as there is nothing in between. That inspired a second method of generating braid words, where each step only allowed generators that wouldn't let the word be simplified by a combination of far commutativity and consecutive inverses, which is implemented by an accumulated band set of generators in the code. In the corresponding graphs for the Jones polynomials, you'll notice the increased variance and tendency to alternate in the shorter braids, which indicates like a higher dependency on length parity. The data is still linear, but with a steeper slope and reaches higher means. We also lose characteristics like the horizontal lines and similarity of two-component links to the overall data. This is one way to demonstrate the importance of choosing the correct method of braid word generation to match the situation, and if I'd be interested in looking at the linking number 2. Anyway, thank you for listening.